radial conduction heat transfer through a hollow cylinder, which could be visualized pictorially as consider a hollow cylinder of radii R1 and R2. K is the conductivity of the cylinder. L is the length of the cylinder. Consider a hollow cylinder of inner radius R1 and outer radius R2. Let T1 is equal to temperature of inner surface and T2 is equal to temperature of outer surface. If we see the cross section of this hollow cylinder, which appears like this, R1, this is R2, K is the conductivity, T1 is the temperature of the inside and T2 is the temperature of the outside surface. Heat transfer is taking place radially outwards from inside surface to the outside surface. If we consider any radius R, consider a radius R and consider an element, a cylindrical element at this radius. Radial heat transfer through this element is given by minus Ka dt by dr. Here the temperature is the function of R. Heat transfer is taking place radially outwards from inside surface to the outside surface. At R is equal to R1 implies T is T1. At R is equal to R2 implies T is equal to T2. Area of element, cylindrical element, is 2 pi RL, area of conduction heat transfer. radial conduction heat transfer at this element is 2 pi RL. That is Fourier law. Therefore, Q is equal to minus K 2 pi RL dt by dr. Assuming steady state heat transfer, Q cannot be the function of R. The Q should be same at every R, otherwise the steady state conditions would not be satisfied. Because if Q is different at different R values, there would be variation of temperature with respect to time. Therefore, to satisfy the steady state heat transfer, Q cannot be the function of R. So in this Fourier law, there are only two variables, temperature and radius. Separating the variables, we get Q into dr by R is equal to minus 2 pi KL into dt. Now, integrating the equation, both sides, R1 to R2, the limits of R, and the respective limits of temperature are T1 and T2. No constant required because it is a definite integral with limits. Q is equal to, Q is a constant, Q is not a function of R, therefore it can be taken out of the integral. Log R2 by R1 is equal to, interchanging the limits, you can remove the minus, becomes plus 2 pi KL into T1 minus T2. Therefore, Q, rate of conduction heat transfer, is equal to 2 pi KL into T1 minus T2 divided by log R2 by R1. So many watts. Therefore, the thermal circuit for this particular case could be given as T1 minus T2. This is a Q. Thermal resistance is RTH. Therefore, RTH is equal to log R2 by R1 divided by 2 pi KL. That is nothing but delta T by Q or T1 minus T2 by Q. So many degrees centigrade per watt. This is the thermal resistance for a single hollow cylinder conduction case. Now I shall consider another case, that is one-dimensional conduction heat transfer through a composite cylinder. That is seeing in the figure. Now let us consider the case of one-dimensional conduction heat transfer through a composite cylinder, which is shown in the figure. Two cylinders, one wrapped around the other, one lagged over the other rather, having two thermal conductivities K1 and K2. The radii are R1, R2 and R3. R2 is the interface radius. R1 is inner radius. R3 is outer radius. Heat transfer is taking place radially outwards. One-dimensional heat transfer is occurring radially outwards. Thermal resistance or thermal circuit for this particular case could be given like this. There are two thermal resistances kept in series in this case, which is given like this. First is radial conduction resistance, then followed by again conduction resistance. Inside temperature is T1, junction temperature is T2, interface outer temperature is T3. That is, at R is equal to R1 implies T is equal to T1. At R is equal to R2 junction, T is equal to T2. At R is equal to R3 implies T is T3. It is series circuit. Heat transfer is flowing in series. Therefore, first resistance is given by radial conduction resistance log R2 by R1 divided by 2 pi K1L. Then log R3 by R2 divided by 2 pi K2L. Therefore, Q is equal to T1 minus T3 divided by sigma RTH. That is T1 minus T3 divided by log R2 by R1 divided by 2 pi K1L plus log R3 by R2 divided by 2 pi K2L. So many watts. This is the heat transfer, radial heat transfer rate through the hollow cylinder. Now consider another case of conduction, convection, radial heat transfer through a hollow cylinder. Now let us consider a hollow cylinder. One cylinder glued over the another. This is the axis of the cylinder, composite cylinder. The inner cylinder is having a conductivity K1. The outer cylinder is having a conductivity K2. This is inner cylinder. Let us consider hot gases inside this cylinder, and outside the composite cylinder that is cold air at T infinity. From the hot gases to the inner surface, heat transfer is by convection H1. From the outer surface to the cold air, heat transfer is by convection with a convection coefficient of H2, watts per meter square Kelvin. L is the length of the cylinder. In this case, the assumptions are: number 1, steady state heat transfer; number 2, constant thermal conductivity values; number 3, no heat generation; and number 4, one-dimensional heat transfer. So, with these assumptions, the thermal circuit would be: there are 4 resistances in series. Between the hot gases and the inside surface, it is heat transfer by convection. Therefore, there is convection resistance between the gases and the inside surface. There is conduction resistance by the inner cylinder, and again conduction resistance by the outer cylinder, and from the outside surface to the outside cold air, ambient air, it is again by convection heat transfer. Therefore, there is convection resistance at the outside surface. So totally there are 4 thermal resistances, 2 convection and 2 conduction, arranged in series. So inside resistance is first convection, conduction, followed by conduction heat transfer, and again convection. So let Tg be the temperature of the gases. T infinity is the temperature of the outside environment. It is series circuit, heat transfer rate is taking place. First resistance is convection. How is that? Given 1 by H1 into inside convection heat transfer area, that is contact area between the gases and the inside surface, given by 2 pi R1L, then followed by conduction resistance log R2 by R1 divided by 2 pi K1L, then followed by log R3 by R2 divided by 2 pi K2L, then followed by convection resistance 1 by H2 into 2 pi R3L. Please note that here 2 pi R1L is the inside convection heat transfer area, 2 pi R3L is outside convection heat transfer area between the outside surface and the outside ambient air. Therefore, the Q is given by rate of heat transfer through the hollow cylinder is given by Tg minus T infinity divided by 1 by H1 2 pi R1L plus log R2 by R1 2 pi K1L plus log R3 by R2 divided by 2 pi K2L plus 1 by H2 into 2 pi R3L. This is the final answer for the steady state conduction, steady state heat transfer through the hollow cylinder with convection and convection. Convection inside and convection outside, in between 2 conductions. Now I shall consider a small problem in which both conduction, convection and radiation, all the 3 phenomena of heat transfer shall prevail. The problem is given like this: an insulated pipe of 50 mm outside diameter with emissivity 0.8 is laid in a room at 30 degrees centigrade. If the surface temperature is 250 degrees centigrade and